Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to our fourth lesson on logic. In the last lesson, we learned about contradiction, tautology, and the contrapositives and converses of a statement. Today, we are going to study quantifiers. We will learn their definitions and their relationships to each other. Are you ready to learn more about mathematical reasoning, everyone? Let us begin. Open statements can be converted into statements by replacing the variable by an individual entity. Open statements can also be converted into statements by using quantifiers. We can use this symbol, there exists or there is, and call it an existential quantifier. Or we can use this symbol and call it a universal quantifier. This symbol represents for all, for every, or for each. Let us use these quantifiers to modify an open statement. There is a natural number x such that x plus 3 equals 9. Written with the existential quantifier, the statement is equivalent to there is some natural number that satisfies property P, or there is at least one natural number which satisfies property P. Written with the universal quantifier, the statement is equivalent to all natural numbers satisfy property P, or every natural number satisfies property P, or each natural number satisfies property P. If we attach a quantifier to an open proposition, it ceases to be open. It becomes a statement with a truth value of T or F. Let us test the use of existential quantifier in our first activity, everyone. Let S equal the set containing 5, 10, 12, 20, 25. P of x is such that x is a multiple of 5, where x is an element of S. Do your best to determine the truth values of the following statements. You can get started now.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, students. Did you manage to determine the truth values of the modified statements? The first statement has a truth value of t. There does exist a multiple of 5 in the set of S. You can take your pick. 5, 10, 20, or 25 all satisfy the conditions of the statement. However, the second statement has a truth value of F. Why? Because 12 is not a multiple of 5, and thereby does not satisfy the condition that all the elements of S are multiples of 5. Was your answer the same? Good work. And now let us study the relations between quantifiers. It is clear that the negation of a given proposition must also be a proposition. Therefore, how can we negate the propositions there exists x for p of x, and for all x then p of x? The proposition for all x then p of x will be false only if we can find an individual a such that p of a is false, which means the statement there does not exist x for p of x has a truth value of t. If we succeed in finding A, then the proposition for all x then P of x is false. We can express this symbolically like this. To find the symbolic form of the negation of there exists some x for P of x, we can follow a similar chain of reasoning. This statement is false if there is no individual A for which P of A is true. So, for every x, P of x is false. Therefore, for every x, the negation of P of x is true. The negation is expressed as there is no x for P of x, which we may write in this fashion. Let us try to apply this idea in our next activity, everyone. Here are 3 statements. Give the negation and determine its truth value for each, assuming that the universe is the set of real numbers. Do your best, and I will see you in a few minutes.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello, students. Have you finished the activity? Then let us check your answers. This is the negation of statement A. There exists an x for which x squared plus 1 is less than or equal to 0. The truth value of this statement is f. Even 0 squared plus 1 is greater than 0, and any other x would yield a higher value than 0. Here is the negation of statement B. For all x, x squared plus x plus 1 cannot equal 0. X squared plus x plus 1 is a prime quadratic function which has no root, so the truth value of this statement is t. You can test this equation using any x you wish, and the answer will never be 0. Finally, this is the negation of statement C. For all x, 4x minus 3 cannot equal negative 2x plus 1. But for the former statement, x equals 2 over 3 makes both results equal, as 4 times 2 over 3 minus 3 is equal to negative 2 times 2 over 3 plus 1. If we take x to equal 2 over 3, we find that each side of the equation is negative 1 over 3. So the truth value of this statement is false. I hope that you found the same answers, everyone. We have time for one more activity. Let U be the set containing 1, 2, 3, 4, and so on through 10. P of x is such that x is an odd natural number. Q of x is such that x is an even number, and R of x is such that x is a prime number. Give the truth values of these three compound statements. Please get started right away.
Students, let's get ready. Begin. Time's up! Let's get back to our lesson.
Welcome back, students. The first statement says, for all x, x is an odd natural number, which implies that x is a prime number. 9 does not satisfy this condition, so its truth value is false. The second statement says, there exists an x which is both an even number and a prime number. 2 is both even and a prime number, so the truth value is true. The third statement says, for all x, if x is not a prime number, then x is an even number. Once again, 9 does not satisfy this condition, so the truth value is false. Today, we have learned about quantifiers. We have defined the universal and existential quantifiers, and we have learned their relationships to each other. In the next lesson, we will begin to study arguments and validity. Until next lesson, thank you, teacher. Thank you, students.